This video is going to be about force time graphs. Force time graphs are useful because the area under a force time graph represents impulse. So for my first example, let's make a force time graph where the force is measured in newtons on the y-axis and the time is measured in seconds on the x-axis. We're going to apply a constant force for some amount of time, and then I'm going to find the area underneath this line that I've drawn. Okay, so the area under this line represents impulse. And so I have a rectangular shape here. So I can find the area by doing base times height. And so base times height gives me force times our change in time. Remember, the force is constant in this example. And remember that in previous videos we found this. Force times change in time is equal to impulse. Now let's look at a more complicated graph. Okay, I have force and time on my axes just as before, and let's apply a force that increases and then decreases. So it makes a triangle. So the area under this triangle is the impulse that would have acted on our object, and the peak of this triangle tells us the maximum force that acted on our object. In example A, the maximum force was the same as the average force because we had a constant force. So I can update our equation. F average is equal to F average times delta t is equal to our impulse. So I'm going to need to modify this equation to find the area under B. So the impulse, and remember this is a triangle, so I'll do 1/2 base times height. And so the height of my triangle is F max, and the base of my triangle is the change in time. Okay, so I have this new equation. Impulse is equal to 1/2 F max times delta t. This is useful for things like a bouncing ball, where the force increases and then decreases, and makes a triangular shape. All right. Usually in real life, you'll have neither of these type of graphs. So for example, if I have a nice curve or something not geometric shaped, how should I handle this? The area under this line still represents impulse, but because my force isn't linear and isn't constant, I can't just use a triangle or rectangle shape, so we can use integration. So my impulse is equal to the integral from time 0 to time t times the force times our change in time. Okay, but in this course you aren't going to be given the calculus option, and so if you're given a non-geometric shape for a force time graph, you need to count the squares under that curve to approximate the impulse to find the area. Yeah. All right, let's look at some examples. So let's do a situation where we have a ball, and this ball is going to bounce two different ways. It's going to have a short bounce or a long bounce. So if I have a 2 kilogram ball moving at 2 meters per second, I have a 2 kilogram ball moving at 10 meters per second, that is going to bounce off this wall, and after bouncing off the wall, it'll still have the same mass of 2 kilograms, but now it'll have a velocity to the left of 10 meters per second. Okay, we're going to have two different bounces. I'll have a short bounce, meaning the base of my triangle is going to be smaller, and because it'll be over less time, and a long bounce. So my short bounce is going to be 0.0002 seconds. And my long bounce is going to have a wider base. It's going to occur over a longer time period. I should state right now that I haven't drawn these to scale. And so the wider base is going to be 0.2 seconds. Okay, so let's look at the impact of having a shorter bounce versus a longer bounce. And I want to look at the impact on the maximum force felt by the ball during the short bounce and the maximum force felt by the ball during the long bounce. So which ball will have a lower F max? So let's derive an equation for F max in general. So my impulse is equal to, so we have a triangle, so I'll do 1/2 base times height. The height of each of these triangles is F max, and the time is delta t. And so impulse is mass times final velocity minus mass times initial velocity, and that's equal to 1/2 F max delta t. I'm going to solve for F max. I get 2 mass times final velocity, mass minus mass times initial velocity divided by our change in time, delta t. Okay, and I can see right off the bat that Fmax is going to be proportional to 1 over delta t, meaning that as time gets bigger, Fmax is going to get smaller. And this makes a lot of sense because if you look at the collision with like a stuntman jumping off a building into a big pillow, that's a long collision, and the reason he survives jumping off the building into a big pillow is because he experiences lower max force, because we make the collision longer. Okay, so let's calculate the difference between the Fmax of these two situations. Let's start with the short bounce, and let's substitute our values in and solve for Fmax. So 2 times our mass of 2 times our change in velocities divided by our time, 0.0002, gives me negative 400 kilonewtons. Wow, that's a lot of force. All right, let's look at the long bounce. Okay, so our delta P is going to be the same. 2 times negative 10 minus 10, because it had the same initial velocity and same final velocity, and it had the same mass, but now it's going to have a change in time of only 0.2 seconds, or a longer time of 0.2 seconds, and that gives me negative 400 newtons, 1,000 times less. Oh, I forgot the minus sign at the top. There we go. All right, and so longer bounce times mean you'll experience less force in a collision. All right, that's the end.